Application of steady flow energy equation in various engineering systems. So we are going to apply the steady flow energy equation in boiler or steam generator, condenser, nozzle, and two types of air compressor. So as we all know, the steady flow energy equation is potential energy plus kinetic energy plus internal energy plus flow energy plus heat supplied to the system on the left hand side or at the inlet side, which is equal to the outlet side potential energy plus kinetic energy plus internal energy plus flow energy plus the work delivered by the system. This is a simple boiler diagram. This is a water tube boiler, and we have a combustion chamber that heats all the tubes, and in turn the tubes boil the water and the steam is generated. So we have continuous water inlet and continuous steam outlet. And we have air inlet in the fuel or the combustion chamber, and the fuel is combusted and the flue is released through the chimney of the boiler. Coming to the application of steady flow energy equation, a boiler is generally used to generate steam at high pressure. So it generates steam at high pressure. The source of producing the steam is the heat that is supplied to the water in the form of any kind of fuel that is combusted in the combustion chamber. So here the heat energy is stored in steam, and the internal energy and flow energy exists because of the flow of water. The heat added increases the internal energy, but there is no work done by the system. So the system here is the steam, so steam is not doing any work. Instead, we add heat, and because of that, steam is produced. So as we can see, the datum height of the inlet and outlet are going to be almost the same because we are going to consider the boiler as one single entity. And the kinetic energy is not going to change because the initial velocity is equal to the final velocity. So we can say the datum height of the inlet and the outlet are equal, and the velocity of the fluid at the inlet and outlet are equal. So we can see in that case the potential energy and kinetic energies get cancelled out, and since there is no work done in the system, so work becomes zero. So what we have finally is Q is equal to, that is heat supplied is equal to the change in enthalpy, that is the enthalpy at the outlet minus the enthalpy at the inlet. The next system where we are going to apply the steady flow energy equation is a condenser. The condenser here is a shell and tube heat exchanger where the cooling water flows through the tubes and the fluid to be condensed is going to flow inside the shell around the tubes. Now let's apply the steady flow energy equation here. So let's try to understand the thermodynamics of the system here. So the device is used to condense hot steam into water by cooling. So heat is removed from the system here. Heat energy is transferred from the steam to coolant. So coolant is going to remove heat from the steam and condense it into water. So as we can see, since we have a heat transfer, we have internal energy, and since there is a flow of hot steam which is condensed into water and then removed from the condenser, we have flow energy existing in this system. And no work is done by the system, which is the steam, and the potential energy and kinetic energies do not change. So we can say that height at the inlet and outlet are going to be the same, and the velocity at the inlet and outlet are going to be approximately the same. The system is not doing any work, so work done is equal to zero. So we can cancel the potential energies and we can cancel the kinetic energies, and finally we have enthalpy and heat transfer because the work done here is zero. So as we saw in the boiler's case, the condenser also has the same equation, which is Q is equal to enthalpy at the outlet minus enthalpy at the inlet. The next system where we are going to apply the steady flow energy equation is a nozzle. So in nozzle, fluid enters at the converging part, passes through the throat, and then in the diverging part, it suddenly expands and there is a pressure drop, and because of the expansion the gas will also accelerate. So because of that, the kinetic energy of the gas increases at the cost of pressure drop. When we apply the steady flow energy equation into a nozzle, so we need to understand the thermodynamical changes happening in a nozzle. Once again, the device increases the velocity of the working fluid at constant pressure drop. So the velocity increases, which in turn increases the kinetic energy, and there is a constant pressure drop. And we can see here, so there is a change in kinetic energy, but no work is done by the system. So we can see the system is not doing any work, but it expands because of the sudden pressure drop. And there is no heat transfer taking place here, and there is no change in potential energy, because as we can see, the fluid enters at the same height and then leaves the system at the same height. So we can substitute work is equal to 0, Q is equal to heat transfer is 0, and there is no change in potential energy. Then the energy flow equation becomes kinetic energy plus enthalpy is equal to kinetic energy plus enthalpy. So we can rearrange and write it as the change in kinetic energy is equal to the change in enthalpy. So as we can see here, so the increase in kinetic energy will result in a decrease in enthalpy in a nozzle. The equation 1 can be rewritten as the outlet velocity square minus inlet velocity square equal to 2 into the change in enthalpy. So to find the final velocity, so we can rearrange this equation and write it as C2 equals square root of 2 into H1 minus H2 plus C1 square. Since the fluid entering the nozzle is going to experience a very high increase in velocity compared to the final velocity, the initial velocity is going to be very, very, very low. So we can neglect it. In that case, we can write it as the final velocity is equal to square root of 2 into enthalpy at the inlet minus the enthalpy at the outlet. And also, the expansion of fluid in a nozzle is treated as a reversible adiabatic or isentropic process. So for a reversible adiabatic or isentropic process, the enthalpy can be given as specific heat capacity at constant pressure into the change in temperature. So we can rewrite the final velocity as square root of 2 times the specific heat capacity at constant pressure into initial temperature minus final temperature, that is the temperature at the inlet minus the temperature at the outlet, plus the square of the initial velocity. And for a reversible adiabatic process, we all know the final temperature is equal to P2 by P1 raised to gamma minus 1 by gamma into T1. So when we substitute this value for the final temperature, we are going to get an expression of final velocity is equal to square root of 2 into specific heat capacity at constant pressure into T1 into 1 minus P2 by P1 raised to gamma minus 1 by gamma plus C1 square. So let's apply the steady flow energy equation to compressors. Compressor is a device that is used to compress air at a very high pressure. So the input of a compressor is atmospheric air and the output is going to be compressed air. Compressors can broadly be classified into two types. The first one being the rotary compressor and the second one being a reciprocating type of compressors. So this is a schematic diagram of a rotary compressor. So as we can see, so there is an external work that is done by using a drive, and because of that, the air that enters at the inlet will get compressed and sent through the outlet. To apply the steady flow energy equation to a rotary compressor, we need to understand the thermodynamical changes a rotary compressor goes through. So rotary compressor uses rotors to compress air at high pressure. So the output is large quantity of air at moderate pressure, not at very high pressure. Because the pressure is not very high, so there is no heat transfer that is going to take place during the compression process. So there is no change in the inlet and outlet's height from the datum. So the potential energy is not going to change. And since the fluid is not accelerated or the velocity of the fluid doesn't change here, so there is no change in kinetic energy. Work is done on the system by an external drive in this case. The whole energy flow equation is going to become H1 is equal to H2 plus W. So in the case of a rotary compressor, work done increases due to increase in enthalpy. The next system we are going to apply the steady flow energy equation is reciprocating compressor. So we can see here there is a piston and a cylinder where the piston is going to compress the air that flows inside because of an external drive which is doing the work of compression here, and the compression is going to be at a very high pressure, so there will be a heat generated in this case. So we can try to understand the thermodynamical changes happening in a reciprocating compressor. So a reciprocating compressor compresses air at high pressure, and the outlet is a very small quantity of air at very high pressure. The compressor is going to have a very large area that is in contact with the surroundings. So because of that, heat will be rejected. So there is a heat transfer happening. So that is, heat is lost to the surroundings and work is also done. Since potential energy and kinetic energy does not change here, so in the equation what is left is going to be the enthalpy at the inlet minus Q because the heat is rejected, which is equal to the enthalpy at the outlet plus the work that is done. So the work done here is going to be equal to negative heat, that is heat rejected plus the change in enthalpy.